Welcome back. Today I'm talking to Nicolás Francisco Lori regarding a Darwinian standard model of physics that obtains general relativity. It's going to be a pretty philosophical discussion today, so if you enjoy that, then this will be very good for you. Without further ado, I think we can get started.
The high level picture, it starts, it has a funny idea, the start. See,
Mhm,
I was writing a book, a philosophy book, and
mhm,
I was trying to look at Darwinism in general. So I was trying to think about what are the philosophical implications of Darwinism. So I had
mhm,
written a work about the I like epistemology a lot. So I
yeah.
have a PhD in physics and I have a PhD in computer science. But the
Mhm,
idea of the theory of information, what information is and how it is processed, is something very important for me. So I published some decades ago a work that I tried to reassess Daniel Dennett's work on free will and the role
mhm,
of information. Then I did another work on how this alters the perspective of Kantian perspective about determinism, because Kant has
mhm,
to do with the fact that at his time there was a deterministic evolution of Newton, which Kant was a physicist. Most people don't know
yeah.
that, but Kant was a physicist, and so he was very interested into Newton's theory, but then he was also interested into the issue of Lamarckism and Lamarck, which also existed at this time. So he was thinking about it, and what I did is that I did a work with a colleague of mine, which was a philosopher, and because I was working in a theory that interests me a lot in quantum
Mhm,
mechanics, which is Zurek's work. I don't know if you know Wojciech
mhm.
Zurek. He had the theory called
He's in quantum Darwinism, no?
quantum
Yeah.
Darwinism. Exactly. So I
Yes.
was very I my work on free will, I think, was the first philosophical work to use quantum Darwinism to
Mhm,
express it, to to make a defense for the existence of a
mhm,
physically compatible free will and
mhm,
what it means. So I was very interested in quantum Darwinism, and I was interested in Darwinism in general, also in the sociological and economical realms. So I did a little bit of economics too. It's, you work in finance, so I was interested. I
mhm.
read, do you know Eric Beinocker's book, The Origin of Wealth?
I've heard of it, but I haven't read it.
Yeah, so I did some work and I read it thoroughly. The Eric Beinocker's work on the origin of wealth, which is a Darwinian interpretation of economics. So
Mhm,
he uses a lot of computer sciences work on Darwinism and tries to apply it to economics with varying degrees of success. I mean,
mhm,
economics is a little bit of a mystery to me. I mean, what gives value? What is the value of something? It's not something that I understand it very thoroughly, but I
mhm,
like it. And so originally I was writing this book, and I was interested in understand. I was trying to propose a general Darwinian theory about everything. I participated in a book that was presented at the École Normale Supérieure about Darwinism for all scales or for all aspects of the universe. So there is this question of if Darwinism can be applied all throughout everything. What I
uh-huh,
noticed is that there was not a Darwinian theory of quantum field theory. So there is no
mhm,
Darwinian quantum field theory approach. I looked for it, and I even invited Zurek to actually see if he wanted to do it. They didn't.
uh-huh,
Nobody was very interested. So I said, okay, so I'm
mhm,
going to do it. So so I started doing it, and my first. So the idea of the work. This is a large preamble, so I'm going to go straight to the idea of the
okay.
work.
That's fine.
So the idea of the work is the following. I was trying to look at a Darwinian approach to quantum field theory, just like there was
Mhm,
a Darwinian approach to quantum mechanics as developed by Zurek. So I was
mhm,
very familiar with Zurek's work, and I've exchanged a couple of emails with him. And I had worked before on issues of applying Darwinism to the Big Bang theory, and but very superficial. But this time, I really wanted to do a Darwinian approach to quantum field theory. And I
right.
remember Feynman's perspective, that it was kind of mysterious to him the huge amount of information that can exist in such minuscule points in space-time. You know, I mean, how can there be so much constants and laws and values of particles in such minute space? So this is the question
Right.
Feynman wondered. And so so the general idea here was that I was thinking, okay, let's imagine I have a Darwinian approach to quantum field theory. Now, there is a difference between quantum mechanics and quantum field theory, in that in quantum field theory, particles appear and disappear. You know, they are created and destroyed. The constants of nature depend on the value of energy. So you don't have like an electric interaction constant. You know, you have the constant depends on the energy of the interaction, because you have this cloud of virtual particles surrounding each particle, and the actual constant that is actually valid will depend on that energy of the interaction. And so I was thinking, but then I was thinking about biology, and I was thinking of the DNA in biology and how the DNA implements and transports the rules. And saying, okay, if I'm going to do a Darwinian perspective of quantum field theory, and if the rules depend on the energy, then the rules must have some kind of local validity. They have to have some kind of local information gathering, so that they can be represented. And so I'm thinking, okay, maybe there's some entity that carries that information. So maybe there's DNA in the cells that carries the laws of life. Maybe there's a kind of cell that carries the laws of physics. And so I called it the physics cell. So the physics cell is like a cell in biology, but instead of being a cell of life, it is a cell of physics. It doesn't carry within it the rules of life. It carries within it the rules of physics. So
Okay. So one question, if I can jump in here, then, is
absolutely.
we're thinking about these cells now as some small constituents in the universe, and as we'll perhaps get into in the paper, we're talking about different spaces. So we're talking about space-time, which is somehow generated by the interaction. I don't want to go too far on that yet, because
Yeah.
I guess we'll get to that point. But then these cells themselves live in an RD space, or potentially an R3 space. Are those two spaces somehow interlinked? Like when we're
Right.
saying, if we're talking about this from the biological point of view, we're saying we have these cells that contain the DNA,
Yeah.
which is somehow the information, and they live sort of locally. I mean, the cell lives in the same space that it interacts with. Are we saying that these physics cells now are embedded in our universe, so to speak, and that you have sort of a local physics within each of these cells, or at least in the surroundings of each cell, or are we saying something different? My fundamental question being, is the statement here that if you take a segment, like a small segment of our space-time, that is somehow populated by these cells, and that there are local physics that could somehow be different if you look at slightly different regions. Is that the
Yeah, that's a
argument?
very
Just so I
good
get it correctly.
point. And actually, you touch upon an issue that, as you can imagine, I didn't stop writing papers. I'm writing new papers about the concept. So
Right.
actually that's a topic that appears on these new papers that I'm trying to submit and publish. And once they get published, I'll definitely show you, so that you can see what I'm working on. But that's actually a very good point. And the reason is that once I started thinking about physics, these physics cells, I started looking about the EPR paradox, you know, the Einstein-Podolsky-Rosen paradox, and the issue of
Mm-hmm.
entanglement. And it struck me that basically what it means that entanglement is trying to say is that if two quantum systems are entangled, they are somewhat outside of space-time. There is an immediacy of that interaction that seems to transcend space-time. And I mean, because they can directly interact or cancel each other no matter how far apart they are.
Mm-hmm.
Then I started thinking about the different concept. Is you use Einstein's special relativity, and you try to put a clock that is attached to a photon that is traveling in vacuum. Okay, the
Mm-hmm.
time stops. So if you actually measure the space-time relativity, you know, the moving of the clock attached to a photon, when it's attached to a photon, the time stops. It's like the photon sees all of its history in the same instant. It's like for the photon, there is no time. There is
Mm-hmm.
time for us, but not for the photon. And you say that photons, for instance, but photons have a certain finite time to travel through time. We can look at light moving across space, but that's for us. For the photon, all of those instants are the same instant. It's like an eternal, permanent now. And this concept of time, which if you just look at Lorentz equations of special relativity, and you make the velocity of the object tend to c, which is the speed of light in vacuum, and you can see that the delta t, the time step, goes to 0. So there is no time evolution for photons. And although photons get slowed by matter, they don't really get slowed by matter. That's an illusion. Photons always travel at the speed of light in vacuum. What happens in matter is that it's harder for the photon to get away from matter. So when they encounter an object, they cannot go in the straight line. They go back and forth and back and forward. And it is that delay in moving across matter that causes the speed of light to change. The speed of the photon does not change. Photons always travel at speed c. But the speed of propagation of the electromagnetic wave associated to the photon is slowed down because of the interaction with matter, because it needs to alter the path. The photon needs to alter its path. So using this concept, I started asking, and because of different conversations I had with some cosmologists, I started asking, is it possible that time is not an intrinsic property of the universe, but rather time is a label. It's a label of communication. And this is where computer science starts, because there's a lot of things. There's an approach in computer science about distributed networks, which has to do with 5G networks and things like that. Which is, if you do fifth generation computation, what happens is that you have objects having local rules of processing, but since they have their own internal rules, and those rules are autonomous because it depends on the manufacturer of each product. So it depends if it's a coffee machine or a refrigerator or if it's a cell phone. It must have a way to communicate what is the type of information representation and what is the thing it does. And that's a communication protocol. Now, communication protocols can be implemented by a global institution like IEEE or the United Nations or Microsoft. They can impose a certain rule and say, okay, this is the rule for this communication. You have this protocol, okay?
Right.
But what if you don't have this protocol? What if you can only build a protocol that each institution is trying to convince the other to implement the protocol? And this is what I did, is that I considered physics cells which have their rules, and they're trying to establish communication protocols. And one of the things, if you look at in some types of computer science, sometimes you don't have the capacity to have all the computer processes occurring at a certain ordered time, meaning that you cannot keep a clock for all the aspects of the computation process. So what you did is that you do allow different parts of the computer system to do it at their own time without having a clock associated to that process. And then you have an external clock that kind of forces the condition of labeling it, of giving it a certain time label above that processing. So I came from this, and I started seeing that space-time could be, and this is the general idea, not an intrinsic property of the universe, but an epiphenomenon property. And so what I did is that I decided, and if my idea is correct, then before there is physics, before there is time, then there is a certain kind of mathematical process that is outside of time. And then I try to look for what is the dimensionality of this timeless process, and that's where R3 comes into place. So the numbers seem to match better if it's three-dimensional. If that timeless system is R3.
Okay. Okay.
Uh,
Let's put the dimensionality to the side for a moment and just linger on the intuition behind the physics cells. So you gave the argument of these information protocols, and you said that you could imagine a situation where the different constituents of this computation, or in our case, then regions of physics, I would say, try to agree on some kind of information protocol without having a higher authority that sort of sets it for you. I suppose that's the idea then for the Darwinian nature of this, right? Like that you're
yes,
saying somehow, and this is where I would like you to paint a bit more of a picture, is you're saying somehow we have these physics cells as sort of the basic constituents at the early universe. We're allowing time to, or time, but iterations of this computational process, let's
yes,
say, evolve. And out of that, we have the emergence of our standard approach to physics or our standard model of
yes.
physics in some way. Would you mind painting the picture of how setting up these basic criteria? So let's take them as true for the second or for a moment that we have these physics cells and we're at the early universe. How would that information exchange lead to something like the standard model of physics?
Like I didn't hear you well.
Like the standard model of physics that we have. So
Okay, the
like
standard model of
the
physics.
yeah.
Okay, the standard model of physics it doesn't include gravity. That's the first thing. So when you talk about standard
Mhm,
model of physics, that's quantum field theory. So our present understanding of physics is standard model of physics, which locally obeys um, special relativity, plus a classical added thing called general relativity that explains
mhm.
gravity, and no one knows how to put them together.
Right.
So that's the present understanding of physics. So when I refer to the standard model of physics, I'm talking about the quantum aspect. So
Yeah.
electromagnetism, electroweak theory, strong nuclear forces. Okay.
Mhm,
So the three of them they assume they are based. I mean, their characteristics are based on gauge symmetries. Specifically, the strong nuclear force is SU3, the weak nuclear force is SU2, and the electromagnetism is U1. So these are
mhm,
three gauge symmetries. Now,
mhm,
once you have those, so these are the three gauge symmetries. So I in this article I was not explaining why do they have to be these three forces, but what I did is that since there is no SU4 gauge symmetry in the standard model of
mhm,
physics, I assume that the highest symmetry that you need is 3. And that's how I guessed that the timeless medium must be three-dimensional.
mhm,
Why? Because I'm using these gauge symmetries. I'm justifying these gauge symmetries as a form of communication protocol between the physics cells. Because their orientation is not specified by a specific parameter, when you're transmitting information, you must be receiving and transmitting information through the quantum fields in a way that is orientation independent, that you can compensate for that. So the representation of your information being received must be independent of the orientation of the physics cells.
mhm,
So if they are independent and if the space is three-dimensional and if they're represented by a complex number, then the natural gauge symmetry is SU3. So that would be the primordial quantum field, SU3. Okay? And
mhm,
then you have
mhm,
other slight, not so generous gauge symmetries, SU2 and U1, which also valid for more simplistic representations. So I'm interpreting the gauge symmetry of the standard model of physics as a form of making a communication protocol between the physics cells. So the
mhm,
quantum fields are gauge invariant so that the communication between physics cells can happen.
mhm,
And the fact that you only have up to SU3 and there is no SU4 gives me a hint that the natural dimension of this timeless medium is 3. So it's R3.
mhm, mhm,
Curiously, if you use R3 and if you calculate the total amount of information that is needed to process a Feynman diagram with 4 vertices for all the standard model of physics, and if you assume Stephen Hawking's, actually the Beck-Einstein-Hawking's relations between how much information you can put in a Planck area, okay, and if you assume
mhm,
that, And if you assume that the processing is done at the surface of the physics cells, this defines a radius or a diameter of the physics cells. And that diameter is exactly the gut scale. So it's the grand unified theory scale. And that is the
Well,
reason.
here comes a follow-up question. Here comes a follow-up question for me then, which also ties back to the question I had before on what space these actually live in. So we could make the case that they live in the same space as we're currently occupying, or we could make the case that they're living in a fundamentally different space. If you're making the case that these physics cells live in a fundamentally different space and they somehow create both the general relativity and standard model of physics in sort of a separate domain, why would the size of these cells in that other domain play a role to begin with? Wouldn't we be able to?
The thing is that
how could we even? Yeah. Okay.
Yeah, I understand your question, and it's very relevant. And the idea comes from the Kantian perspective between the phenomenon and the nomenon. So the thing that you can extract about something and the thing in itself. So the idea here is that what we actually see and observe is quantum fields. So our reality, our physics interactions, our beingness is the quantum fields being communicating and received. But when the quantum fields, when they interact with the physics cells, they must be transported. They are being transported. So there is a physicality to those physics cells. So those physics cells exist on this timeless R3 medium. But we, as people, are the result of those quantum field interactions between these physics cells. So you have this R3 timeless entities that in their interactions, there is a label on the interactions between these timeless entities, and the label of the interactions between those timeless entities is the space-time label, which has the space and the time label. So although those entities exist in a timeless mathematical 3D medium, if you want, it's almost it's a mathematical medium. It's a timeless mathematical medium. The quantum field interactions between those entities have space-time labels, which is what we call the space-time. So they have a physicality, they have a volume in R3, but they have a communication time label associated to their interactions. And so their iterations, their mathematical iterations, for us, they exist in time, because when they occur for us that are interacting through the quantum fields, there is a time label you can associate to them. But they are in a certain way outside of the physical realm, in the sense that it's like when you're in the internet. Okay, so if you type, you're communicating through the net, there's HTTPS, which is the communication protocol that allows this for occur, but you don't affect the communication protocol. There's no way you can affect the way the internet is built so that you can transmit this and you can receive this, but you don't affect the HTTPS code. You are not allowed to. There's no way you can. There's nothing you or me can do to allow this. There are people in the case of this network that are allowed to, but they are very high up in the scale of the network infrastructure, so that they could affect and alter the communication protocol. So, so we are not, we as physical entities, we are not at the level of affecting that communication protocol. So we receive a time label from entities who have no need for that time label. They only need that time label for communicating between each other. So that's the idea. So they exist in this space-time, and it means that their communication is what creates the space-time. So it's not that they communicate through the space-time. Their communication is the space-time. But they themselves do not require the space-time to occur as they occur in a timeless medium. So that's a general idea.
Yes. do you have any argument for, like, you're saying you're creating space-time as these physics cells interact, and consequently, I would say we're all then as physical beings part like constituted of the, let's say, product of these physics cells.
Mhm.
Additionally, so like as you're interacting with the world, arguably then you're interacting through this communication protocol, and you hence receive some information that is along the rules of that communication protocol.
Yes.
For the physics cells themselves. Like, so we're interacting then, let's say, within the confines of this interaction protocol, which gives us the physics, and
Mhm.
anything that exists outside of that communication protocol, I would argue we simply have no clue what the physics would be. So my, let's say, trying to play devil's advocate in this would be to say that, okay, we have this estimation now for the size of the cells that are somehow in another domain, but
Mhm.
how can we say anything intelligible about the physics in that domain if we're saying that physics itself is something that arises from this generic communication protocol?
Well, that's a very good question. I would just correct one thing. What happens in those physics cells would be more akin to mathematics or computation than to physics.
Uh-huh. Okay.
So, it's more like computational mathematics or mathematical
Uh-huh.
computation.
Uh-huh.
I mean, given what we study in our
Yeah.
culture, it'd be more similar to that.
Uh-huh.
I have worked with a colleague of mine on ways of representing R3 continuous domains in discrete fashion as a limit
Mhm.
of serial of an evolution of discrete systems. So
Mhm.
so if something happens, then it might be I would guess I would extend Darwinism beyond physics, and I would go extend Darwinism into mathematics, and
Yeah.
it would be like a timeless evolution of mathematical complexity, moving from simple trivial mathematics into more advanced mathematics until the physics cells occur. So the physics cells
Uh-huh.
would be the expression of an already advanced mathematical system within a physical realm. Before that, it would just be a timeless mathematical evolution. And people
Mhm.
sometimes have a confusion that how can be something occurring and without time? Because everything that we see happens in time. So what is the meaning of something happening without time? My parallel would be like imagine you're adding something like you have 5 plus 7 equals 12.
Mhm.
You can do that calculation with your head and with your head or with your hand, and it happens in a certain time. But the time is just a label that you add to the writing of that phenomenon. The phenomenon
Uh-huh.
itself of the 5 plus 7 equals 12 does not need in any way time or space or matter to exist. It just requires a location of information representation, if you want. But it doesn't
Mhm.
really require time. Now imagine you have a computer. Now imagine you're asking computer to make all sorts of mathematical calculations, like in a video game. Now,
Mhm.
you can have a computer that you are following each calculation, and you make sure that if you have like 10 parallel processes, that parallel process 1 only occurs, the next step of parallel process 1 only occurs if a step alpha of parallel process 7 occurs. So you can have
Mhm.
parallel processes that somehow each time advance depends on the time advance of the other, so that a certain time
Mhm.
reality exists. You can make that, but then your processing becomes a lot slower. That's not what
Mhm.
computers do. Computers don't care. Each parallel process advances on its own, and they communicate at the end what the final product is. That is like a
Right.
timeless calculation, in the sense that each of the
Mhm.
aspects do not need to have a time label to do the thing. They just do their own calculations. They add objects and they subtract each one individually, and then they converge. That form
Mhm.
of timeless computation is possible in our computers. So of course you can say, well, there is time and you can, but for the computer, there is no internal clock when it's doing those calculations. So
Mhm. I mean, I think that argument is fine, right? I don't feel like we need to stick necessarily to the concept of time. Like, if we have, you're approaching this very much from a computational point of view. And as far as I see it, you could think of the physics cells pretty much as a class in object-oriented programming, if you will.
Yes.
And then you have these classes that are just interacting according to some scheme, let's say, and that gives rise to the rest of the physics. I don't see why we necessarily need to introduce a size of these physics cells. Like, I would be fine, at least like based on what I heard now, to think about these as classes in the object-oriented sense. Like, they don't necessarily have a size. It's just a mathematical abstraction of some sort, and then the communication between those then gives rise to the laws that we see.
Right. Size happens because of the idea of Planck scale and the limits of what we can observe, for instance, in the surface of the black holes and all the study that Hawkins and Bekenstein and others.
But then you're taking so here's my problem with that. You seem to be taking the physics that we now observe, arguably as a consequence of this Darwinian evolution, and then imposing that back onto the original communication protocol. If you're saying that these two are two fundamentally different spaces, I don't see how our knowledge of, let's say, information storage in black holes has anything to do with this alternate space that, let's say, operates according to some fundamentally different set of rules.
Right. So what I'm thinking is that, okay, let's assume we have no idea on how physics cells operate, which is valid.
Yeah.
But let's say that we know that, there's certain information coming in and certain amount of information coming out. We know that there are different mechanisms in physics to calculate that interaction. For instance, in classical physics, you have Newtonian, you have Hamiltonians, you have Lagrangians. So there are different ways that you can represent exactly the same physical interaction by choosing different variables. Likewise, when you have quantum field theory, there's also different ways you can represent, although usually you use Feynman diagrams, which is a generalization of Lagrangians. Of Lagrangian densities. So you use Lagrangian densities, locally valid, to process those interactions. So what I was thinking is that we know this physics reality occurs if those physics cells entities are calculating this through some mechanisms which I have no idea about, but they have the same constraints on having some information coming in and some information coming out. If I put the limit of information of what amount of information can come in or come out at the surface, which has several mathematical reasons why that has to do why that limit occurs, and let's say that at the surface of the physics cells, the part where the physics cells interact between each other through the emission and reception of quantum fields, that I put those limits, okay, and I calculated everything, all the information that needs to occur for a Feynman diagram with a full standard model of physics to be calculated. And using those rules, I calculated a diameter. And now that's a curious thing, is that the size of that diameter, so the physical diameter that we in the physical world would ascribe to a place where a processing is occurring, okay, the size, why does that size matter to us? Since we cannot enter the physics cells, it matters because there's not a wavelength below this cannot exist. And when you have a pure state in quantum mechanics, wavelengths and frequencies are very important. And so there is a time step below which time discretization cannot go on. There is a time length below which you cannot go. And since there is a time below which you cannot go, because you would have no way of processing that amount of information. It would be too much for the physics cells. So the physics cells, although they have a huge computational power, they is not infinite, which answers Feynman's question. What is the maximum computational power that you can process through physics? And the physics cells gives an answer to that. Okay? And now since you have that, and you ask, what is that scale? Does that scale make sense? And that scale is actually the gut scale. The gut scale is the grand unified theory scale. That's the scale at which the three forces of the standard model of physics converge. Meaning that they obtain the same value. They became identical. This is the scale at which the three forces become the same force. That's the gut scale. And so I have an idea. Maybe the reason for the gut scale is the finite size of the physics cell. That's the scale from which all forces, interactions come from. So it's a mathematical coincidence that if you assume the entire, because there was no reason for this to work. Okay.
Right.
Because think, you're calculating the entire information processing of all the three different interactions, all the qubits that are necessary in a Feynman diagram with 4 vertices, which is the fundamental Feynman diagram. Okay. So you calculate this. Then you start using the Bekenstein-Hawking formula associated with how much information can be stored in the surface of a black hole. Okay. And then you apply this to a physics cell and you say, okay, how big is it? How big is it? Well, that depends on the dimensionality. If it depends, it's 2-dimensional, 3-dimensional, 4-dimensional, medium. But since you only have SU3 as the maximum gauge symmetry, that's a good reason to propose that 3 dimensions is the dimension of the medium. And if you use those 3 dimensions, and you use the amount of information of the standard model of physics, and you use the amount of information stored in the surface of a black hole, and you cross all that, you obtain a size. You obtain the size. And that size is the same as the gut scale. The gut scale is when the coupling constants of the strong nuclear force, the weak nuclear force, and the electromagnetic force assume the same value. Now, those are 2 very different ways of calculating the same size. And the fact that they are the same size is a huge coincidence, because this work for me started as a toy model. When I first started doing it, I didn't believe in it. I was just making a toy model, a Darwinian toy model of quantum field theory, just to show that it was possible. That was it. I just wanted to show that it was possible. Like there was Darwinian quantum mechanics, it is possible that there is Darwinian quantum field theory. That was all the goal of what my calculation was. The reason that grabbed me is when those 2 forms of convergence of the size, using the changing value of the coupling constants for different amounts of energy, and the amount of information that the physics cells needed to have to calculate the standard model of physics within a 3-dimensional medium, the fact that they are the same value. I mean, they are not the same value within 2 orders of magnitude. They are the same value within 0 orders of magnitude. It's like a factor of 2 or 3. In quantum field theory, having things of the same order of magnitude is amazing. It was absolutely amazing. And so I said, okay, maybe there is something there.
I think the theoretical aspects of this I'm not really able to opine on, like whether or not the limits imposed by this are of the same order of magnitude. I'll simply take your word for it for the moment.
I mean, the calculation works, but yes. I could be wrong. I mean, I could be wrong.
The part where I would like to get back to is around the core of the idea as well, because we discussed this now from one perspective. We discussed how there seems to be a coincidence in terms of the scales that we get from the mathematics that are derived from these physics cells, and that's one part of it. The other part of it is the Darwinian side of this entire framework, and we haven't really discussed that yet. So I would like to also transition a little bit to discuss that.
Let me talk first about Darwinian quantum mechanics. Darwinian quantum mechanics, which is quantum Darwinism of Zurich, what it does is it's about the decoherence process, which means how quantum physics becomes classical physics. So how a system that can exist in a multitude of states assumes a single state. There are multiple ways of doing this, but usually the approach that is used in quantum field theory is the multiverse. So the usual option, the usual solution to this approach in quantum field theory is saying there are multiple universes, and each time there's a quantum measurement, there's a choice of a path. So you choose a path where this spin up versus spin down occurs. In one universe you have the spin up, and in the other universe you have the spin down, and all those things need to occur. And that's Alan Gould's approach. That's what he uses for the cosmic inflation approach. That's Everett's many worlds approach, and so that's what usually is assumed. The Darwinian approach of quantum mechanics is different because it says that the other worlds do not exist, they become extinct. So,
Okay.
so that's the basic difference between the average many-year-old approach and the quantum Darwinism approach. The thing is that in the average many-world approach, it's usually what is used in quantum field theory, and whereas the Darwinian, quantum Darwinism is more approaching quantum mechanics. Now, the difference between quantum mechanics and quantum field theory is usually to do with the range of energy that is being associated. So when you're talking about quantum mechanics, you're usually talking about chemistry, like Niels Bohr atom, hydrogen, molecular interactions. You have 300 degrees, 400 degrees, or you approach the 0 degrees. It's different when you have quantum field theory, that's usually high energies. So when you atomic bombs, CERN, nuclear reactors, so you have very high energy particles interaction. So they are different approaches to physics that cover different aspects. Now, what happens in quantum mechanics is that you usually can use Hilbert spaces. So you have eigenstates, which are classical states, and you can represent the system as a superposition of those states. And what happens in a measurement is that out of all those different states, only one comes, which is the measured one. Okay?
Right.
But if you use the average many world interpretations, what happens is that they all exist. So all the worlds, all the universes exist. And so what you do is that you just take a path. It just happens that you go through one path or through the other path. The reasons why conceptually this is important, you see, the average many world approach is deterministic because the Schrödinger equation is deterministic. So if you look at the Schrödinger equation of quantum mechanics, you have determinism. So it only evolves in a deterministic fashion. The non-deterministic aspect comes out of the measurement process. But in the many world approaches, in the average many world approaches, since you don't really have a measurement process, you just choose a different path. Each of these, so the set of all the paths is still a deterministic approach. It's just a multi-deterministic, but everything is determined. In quantum Darwinism, like in Darwinism in general, you don't have the determinism. You have the random elimination of some of the aspects of it. So what I was trying to do in this approach is that I was trying to get this Darwinian extinction component and put it into quantum field theory. So
can we talk a little bit more on how that extinction process works, like in the context of a measurement? So the average many worlds theory, I think that's clear. You have a branching out process, and then we, let's say, exist in one of these, and what we can observe is one instance of this. What would be the selection criteria? And I know that would be sort of a heuristic selection criteria since we're looking at this from a Darwinian perspective, but what would be the selection criteria for a Darwinian approach to the measurement problem?
Well,
is there a natural selection for? Is there a selection process
it
for
is
what
a
would be
natural
more
selection.
desirable
What
than something else?
happened is that Zurek used the concept, which I think is a very interesting philosophical concept, which is epiontic. So usually in philosophy, you separate the ontic aspect, which is the thing in itself, from the epistemological aspect, which is the capacity to transmit information about the thing. What Zurek proposed in his quantum Darwinism, which actually the original name was quantum existentialism, and then it became quantum Darwinism. So the first name he gave it was quantum existentialism, and what he did was that he considered that if the universe is fundamentally epiontic, it means that the ontic aspect of it, so its own existence, only can exist through the transmission of information. So in the epiontic aspect, the thing does not exist independently of its capacity to give information about itself. It is the capacity to give information about itself that allows its existence.
Okay.
And so what happens is that in that sense, it's like if you think reproduction, is giving information about oneself as a biological entity, or in the kind of network memes, the capacity that information about something is transmitted to a different set of links that gives existence to that entity. So it's in that sense it's an existentialist philosophy, in the sense that you don't exist on itself, and the transmission of information is something independent. The transmission of information is it what allows the survival of the thing in itself. So when you are measuring a quantum system, and you have all the possible states, like you have spin up or spin down, okay, as the interaction between the system and the environment occurs, as the light is being transmitted information, the labeling of that information in the environment makes it impossible for the two different states to coexist. So if it doesn't provide information, then the system isolated can be in the pure state of up plus down, okay? But as the information starts going out, that becomes harder and harder. So this one of them becomes stronger, and the other one starts dissipating, okay? And the more photons you give to the environment, the more this one dissipates, and the stronger this one remains, okay? And eventually, all you get is this. And this is a continuous process that is associated with the amount of information being transmitted. But it goes to it goes with the, if I remember correctly, it goes with the exponent of the fourth power of photon numbers, of the number of photons. If you remember math, the exponent of a fourth power, it really goes to zero really fast. So the disappearance of this other branch is very fast. And the idea of Darwinism is that this disappearance occurs. So it's a breaking with determinism. So what Darwinism allows is a conceptual breaking from absolute determinism. Because one of the things that,
if I understand it correctly,
just a mathematical comment about something that is unrelated with this, which is the following. Darwinism is evolution. Darwinian evolution is non-deterministic. So there's actually some work indicates that is really not possible to predict which is the next species that is actually going to become extinct. And so that surprising capacity, at least there are some mathematical indications of that, science is always advancing and evolving, but there is indication of that. So what I was trying to do with this Darwinian approach to quantum field theory is to allow for a breaking with absolute determinism, with the idea that absolute determinism is necessarily a definition of science or a definition of the universe.
Okay, so I was wondering where we now take the step from quantum Darwinism to the kind of Darwinism that you're suggesting now with these physics cells. We discussed how in the quantum Darwinism setting, my understanding of that is it's similar to, let's say, an inverted pendulum. You have, at the time of measurement, sort of an inverted pendulum situation where if you imagine two possible outcomes of this measurement, it will flip to one way or the other. And the circumstances are set up in such a way that it will necessarily take one side or the other. It's also set up in such a way, depending on the experiment, that let's say you have a 50-50 chance. Well, it's non-deterministic in which outcome you're going to get, but nevertheless, the experiment or let's say the setting of this, the environment surrounding your measurement is set up in such a way that you will necessarily have this inverted pendulum kind of situation. Now, I would just like to understand, where does your theory of Darwinism in this physics cell approach connect to the quantum Darwinism that we just discussed, if at all?
Well, it connects directly in the sense that it's inspired by it. And it also connects with the issue that when you're thinking about the preparation of the pendulum, okay, the problem is that when you're preparing the pendulum, there is an intrinsic Heisenberg uncertainty in position versus momentum. And in the communication protocol within the physics cells, the way the communication about location and momentum is transmitted, it's also always in a way that Heisenberg uncertainty is implemented, so that the uncertainty of the quantum physics about Heisenberg uncertainty is implemented in the communication of the protocols. So the randomness, the intrinsic randomness, is within the communication itself. It's the way the information is being represented, either through because the basis of the Heisenberg uncertainty principle, if it's a wave representation, you either pack it in having it a very short range of frequencies or a very large range of frequencies. But whichever way you prefer, you either have uncertainty in position or you have uncertainty in momentum. You cannot have certainty in both of them because it's represented by waves. So that wave representation within the communications of the physics cells guarantees that Heisenberg uncertainty occurs. So the randomness exists. And so if the randomness exists, and if the laws of the standard model of physics are implemented as the Lagrangians that I am being assuming that are somehow represented within the physics cells are the same Lagrangians as the standard model of physics, or at least very similar to the ones we now know, then when those objects interact, then they approximately will make that pendulum converge to one of the sides and force that solution. What happens is that using the epiontic perspective of quantum Darwinism is that as that information is transmitted, the existence of the other solution that is not measured is extinct. It disappears. There's not another universe where that information exists. It's lost. It's gone. Now, there is a trick you can do in quantum mechanics. It is lost as it spreads throughout the universe. So if you have a larger box, you can somehow reverse this and recover that information because that information is being dissipated away, disintegrated into the universe. What happens is that since physics cells have a finite size, if to store that information, the wavelength is smaller than the physics cell, then the information is irretrievable. So once you pass a certain size, once the wavelength passes a certain size below, so the wavelength becomes lower than a certain value, or the frequency becomes higher than the maximum frequency that can be represented in a physics cell, okay, then that information is irretrievably lost, which means that if the bodies become large enough, or meaning massive enough, then you can no longer represent the pure state associated to that object, and the object becomes classical. So the object becomes classical because that information is not possible to represent within a physics cell. Just one note, the actual value, there was a little bit error of a calculation. The actual value is 7.6 times 10 to the minus 12 kilograms, not 7.9. So there was a rounding error in the original publication, but then the publication that came afterwards that corrected that approximation error. But so it's 7.6. So any object that is heavier than 7.6 times 10 to the minus 12 kilograms cannot be represented as a pure state in quantum mechanics, which implies a limit in quantum computation.
Okay, but let's again think back to the three components of Darwinism in general and see how they relate to the physics cell. So first of all, we have some variation of the laws, like in the context of biology, this would be variation to the DNA. Then you have selection of the fittest variants, and then you have some heredity or retention of those genes, let's say, or whatever we want to call it. Now, we're saying, or as far as I understand, you're making the argument that these physics cells are evolving according to this process, and that the thing that evolves is the physics associated with this cell. So you represent the physics in your paper by psi, I believe it is, and there would then be some evolution of these physics. Like the uncertainty would not be, let's say, contained in the uncertainty principle, which is somehow a component of this physics, of this psi, but rather there would be a variation of psi itself, or the physics itself. What are those criteria that you're setting up to ultimately arrive at this standard model of physics as a result?
Well, the idea, and it first appeared this similar thought in a previous work I did with a colleague, is that during the time of cosmic inflation,
Hmm.
There is an accelerated alterations of the physics laws. So a certain aspects of physics is favored. So it
Hmm.
happens very soon after the Big Bang. So somewhat between the first time steps of the cells and until cosmic inflation. That's more or less the time period where physics stabilizes. So,
Okay.
and now what happens is now you can ask the question, how stable is it? And so there is
Well,
some
before
work
that, I would
into.
like to ask the question. Before I would like to ask the question, not just how stable it is once it converges, but how is the convergence process actually taking place? Are you saying that the physics cells somehow have a lifespan attached to them, and that they can somehow like reproduce, if you will, in the classical sense? Like, how does the physics actually evolve in the setup? What is the renewal process, if you will, that causes it to converge in the first place?
The honest answer to this right now is I don't know, because I
Okay.
I I have no idea. I mean, I'm as I'm assuming that they do evolve. I think that a
Uh-huh.
reasonable location in space-time for that evolution to occur would have been the time of the cosmic inflation. The
Uh-huh.
reason for that is that after the cosmic inflation, the separation of the components of the universe would be too big for that
Hmm.
evolution to basically continue. And so it seems that the laws of physics seems to be quite homogeneous across the universe. So if there was some lack of homogeneity, it's probably the likely period to occur is that period of the cosmic inflation. There is I did some work about the Big Bang and quantum Darwinism, where I mean it was just very simple calculations, but that the time that if you consider that the universe bubbles that existed during the time of the cosmic inflation, they obey rules similar to a diffusion process. And if you make a parallel to the same diffusion process that occurs in quantum Darwinism, and then if you make the kinds of calculations, so you infer a time, then you get that the cosmic inflation is long enough so that a process of homogenization of the coherence, of the decoherence, of the quantum Darwinism associated with that process is shorter than the time of cosmic
Hmm.
inflation. So I did some work in 2009, 2010 about making this calculation that somehow it makes sense. Now I'm trying to redo some of those calculations back again with a new theory, because this theory didn't exist then. So I did with the theories that I had. Um, so I would say cosmic inflation is a time
Hmm.
where the physics cells come from a random possibility of different ways of perspective of physics until they get somehow homogenized into um, a standard model of physics that is common for all the physics
Hmm.
cells. How this process happens? Um, does the physics cells change in size? Do the physics cells mutate? Are there different types of physics cells? Do they all converge to one single type of physics cell? I mean, those are very interesting questions. I think we would need to know a lot more about what the process is going on at the cosmic inflation time to actually know
Yeah.
what
Uh-huh.
happens. We don't know. Um, could there be, for instance, physics cells of slightly different size, like bacteria and viruses? I have no idea. I mean, the way I look at this
Hmm.
is like if this model is true, I mean, and if I'm correct, um, then there is a lot of wealth of processing that is occurring beyond physics. So this is in some way beyond physics in the sense that is beyond time, and so this would be like theoretical mathematics, theoretical computational mathematics, on thinkings of how those things could exist. Maybe in some house it's I mean, in some ways it would be unresolvable in the sense of in the sense that all we can have is an average behavior of such physics cells, and there are different populations of physics cells that could all describe similar phenomenon. I mean, we're just starting. I mean, these are very recent works. I'm just surprised
Okay,
that this is possible at all.
let me ask this then, and this could be a good question to round off the interview with as well. If we look at your research now and the many directions that you've articulated now that you could take the research, what is most pressing from your perspective? What are the things that, expanding upon this now, you would like to investigate, let's say, immediately?
Well, I think a question is if pure states in quantum mechanics having wavelengths smaller than the physics cell size are possible or not. I mean
Uh-huh.
that is what I would say, and this is a very detailed issue because even if you are working in quantum computations or in quantum computers, you you often don't need an absolute pure state in the sense that if you have a system that has some wave-like characteristics and some amount of superposition, that's good enough. So you don't have to be overly demanding on being an absolutely pure state. Absolute pure states are very hard to build and implement. They require very low temperatures and very strong stability. Um, Now, I looked when I published my most recent work, what were the biggest size of pure states that have been built
Mhm.
and what are their corresponding masses, and they're still below the PC size value.
Mhm.
So for now, my PC approach can be theoretically valid in the sense that those thresholds are not overcome. I think it's Brian Greene, who is a computer physicist that works in quantum computations, and I hope I didn't get his name wrong. But but the thing is that I mean, we talked in the conference, and the question is, there's a lot of effort of doing quantum computers that assume that pure states, which are necessary for quantum computation, can exist at any mass, provided you isolate them enough. And I'm claiming
Mhm.
that it is not possible. I'm
Mhm.
claiming that above a certain mass, if the wavelength associated with the pure state goes below the PC size, the pure state will not hold itself. And so there is a limit to what quantum computers can do. And that appears actually in the paper. So I propose the limit to the maximum qubits that a quantum computer can have. Um, if I am correct, I think that the first experimental measurement to show that I am correct or not will be when they try to reach that pure state with very large mass, but it has to be a real pure state with very large mass, and if they succeed or fail, that will, I think, will be the experimental test. And imagine they fail, but at a different value. Say that that at the PC scale, that that still works, but if we make it 5 times the PC scale, then it fails, or 10 times the PC scale, then it fails. It fails at a different point. Then a new theory would have to be proposed to explain why it failed at a certain point and not at the other. But my theory is that classical states exist because the computation required to have a pure state with arbitrary mass is too large for the physical universe to implement such a computation.
Okay, time will tell, hopefully. Good. I think we can wrap up the interview here. I don't know if there are any final statements that you would like to make before closing, like to the research community or
Uh,
anyone who's interested.
I would like to thank you for a very nice interview. I'd like to thank you for the idea of this this topic that you're presenting. So I'm very thankful for
Likewise.
being invited, for having been invited, and and so and I'll be glad to interact with you and ask and answer any other questions you might have. Imagine that you say, "Well, I didn't understand this. Can we ask this and answer this?" I'll be glad to do that. And I like your questions a lot. So thank you for reading it and thinking about it, and asking those questions. And as you said, time will tell if this theory is is the actual thing or not. But that's the fun of theoretical physics.
Yes. Likewise. Thank you very much for taking the time. I appreciate the discussion and I had lots of fun. So, yeah, thank you.